Welcome to the session on hierarchical modeling in Verilog. So in this particular session we will be seeing the two design methodologies in Verilog. We also will be seeing what are the rules governing the connection of ports when we connect one module to the another one. We will be seeing the hierarchical modeling examples. Basically we will be discussing two methods of instantiating or reusing a module to build a larger module. There are two methods. One is by instantiation by port name and the other one is called instantiation by port order or by port position. We'll be seeing examples on each one. We also will be seeing how the concept of test benches can be put to use for design verification. Now when we talk about the design methodology supported by Verilog, we can go for top-down design methodology as well as bottom-up design methodology. Both are very intuitive. In top-down design methodology, we first go about describing the top-level block. Then the designer will identify what are the most optimum sub-blocks that need to be connected to achieve this top-level description. And the sub-blocks will be further divided into sub-blocks till we reach something called a leaf cell or the smallest building block. Okay. So this, for example, when we are going for a designing of a processor, we will be first designing describing the processor IOs, then we will be describing a data path unit as well as a control unit that support the instruction set architecture. Then within the data path unit we will decide what kind of ALU should be going in, what kind of adders will be going in, what kind of registers will be going in, and so on. So that comprises the top level block. On certain other occasions we are highly concerned about the performance at the macro level, so we will be designing the leaf cells in the most optimum way. When we talk about optimum way in VLSI, basically we may mean PAP optimization, reducing the power, reducing the silicon footprint or the area, as well as increasing the performance. Okay, so ultimate care will be given in leaf cell design, and such leaf cells will be very optimally used for building macro cells or modules, and those modules will be stitched together to build a high performing top level block. So that comprises the bottom up approach. Now if you look at module as we have described is the smallest building entity in a Verilog program or description. Module serves like a template for creating new objects. Okay, so the module, once instantiated or invoked, it will create a unique object from that template. And this process of creating a unique object from a module already in place is called module instantiation, and the newly created object is called a module instance. Each module instance can be given a unique name, can have its own variables, parameters, as well as IO interfaces. Now let us touch upon what are the different rules governing connecting the ports when we perform hierarchical modeling. That is, whenever we are connecting a module to another module, those ports which get connected should be following certain rules. For example, the input port of a module, as you can see in the figure, the input port of a module must be declared as a net data type. The typical keyword for that is wire. Okay, whereas it can be driven from an external port, which could be either a net or a register. Okay. Similarly, the output port of a module can be a register or a net, but it can drive only a net in the external world. When you are connecting an output port to another port of input in nature, it will be connected to a net data type. Similarly, whenever you are connecting modules, whenever there are interconnection or whenever there are inter-module connections, width matching is very, very important. Okay, it is illegal to connect an internal and an external item having different sizes. For example, this output port, suppose it is of a register type and it is having, say, 8-bit width. It need to be driving a net having the same width of 8-bit. Otherwise, there will be an interconnection error. There will be a width mismatch error. So these are the important port connection rules that must be strictly followed while we are describing modules in Verilog. Now to emphasize the hierarchical building concept, let us look at this example of a 4-bit adder. As we know, this 4-bit adder, if we start describing the 4-bit adder, it can be further be comprising of 4 1-bit full adders, which can be in turn built from say 2 half adders, which in turn can be built out of modules like logic primitives, XOR and AND. Okay, so if you follow from the 4-bit full adder, we can call it as a top down. On the other hand, we can also have a bottom up approach. Okay, now let us take this simple example. We understood that to build a 4-bit adder, the bare minimum we require 4 1-bit full adder. I am talking about structurally building this 4-bit full adder. So let us first examine the description of a 1-bit full adder, and therein we will procedurally build from bottom up a 4-bit full adder. Now this is a description of a 1-bit full adder. You can see here it has 3 ports A, B and C in, each having 1 bit width. Also it is having 2 ports sum and C out, having 1 bit each. Okay, so as the module description goes, you have module name, list of all ports which are A, B, C in, sum and C out, and the input ports are A, B and C in, the output port is sum and C out. Then the functionality, we know that sum is nothing but A XOR B XOR C in. This is how we XOR variables in Verilog, this particular operator, as we have already discussed. Similarly, the C out is nothing but A ampersand B ORed with B ampersand C in, ORed with A ampersand C in. Okay, so that describes completely the functionality of a 1-bit full adder. We are good to write the end module. So this description is for a 1-bit full adder. Now we are going to utilize it 4 times so as to build a 1-bit full adder, and the structure for this will look like this. We can have 4 instances of 1-bit full adder, which we have already seen right now. Let us label it as FA0, FA1, FA2, FA3. Okay, so if you look at a 4-bit ripple carry adder or a 4-bit adder like this, it will be having basically ports capital A, capital B, capital C out and capital sum. Okay, capital A, capital B, capital C in, capital C out and capital sum. Okay, I am just given it capital and small letter just to distinguish, help you distinguish the ports of subunit as well as the top level block. It is not mandatory to do so, but just for easy distinguishing. All the small letter ports are the ports of the sub block called 1-bit full adder, and all the capital letter ports are representing the ports of the top level called 4-bit ripple carry adder. Now please keep this structure in mind while we discuss the program. So before we move ahead, we also have to see the syntax of how the ports are connected during module instantiation. You please look at this example. Whenever you have to instantiate a particular module, we have to write the name of the module. Okay, so here Verilog 1 represent the name of the module which we have to instantiate. Okay, so in our case, what will be the module? In our case, we have to instantiate full adder, 1-bit full adder, right? So whatever is the name, I have given the name FA. So here I should be writing FA. Then my Verilog is an instance name. It is just like a label which I assign to my instance. So it can be any name, it could be even your name. Okay, so first name is fixed once you design the sub block. Second word is an instance name. Then we have to put a bracket, put a dot and write the name of a variable of the sub block. Okay, so here A, B and C represent the port name of Verilog 1 module which we are trying to instantiate, and what you see inside the internal bracket are the corresponding port of the top level block. Okay, so in this particular example, if you look at, we can see, you look at FA0, the port A of my 1-bit full adder FA0 is getting connected to the port A of 0 of my top level block. Similarly, port B should be connected to B of 0 of my top level block. Okay, so this is what we are going to write here. So this kind of instantiation is called module instantiation by port name. Okay, let us see how we can accomplish this while we write the 4-bit full adder circuit. Now please recollect, this is the 4-bit full adder we are trying to describe. So as normal, we have to write the module name, etc. Module is the keyword, then the total for ripple carry adder I have given the label RCA. Then inside the bracket I am listing out all the ports. The ports are capital A, capital B, then capital C in, capital sum, and capital C out. Now I have to do the declaration of input port and output port. As you can see here, the ports A, B are input ports having 4-bit width, whereas the C in is also input port which is having only 1 bit. So I have to declare it separately. Okay, A and B I have declared as vector port, C in as scalar port, but all these 3 ports are input in nature. So I have to describe it separately, that's all. The next step is sum is a 4-bit port and C out is also a output port but having 1 bit. So I have to declare it separately like this. Both are an output, sum is 4-bit wide. Now having done the port declaration, I am good to write the module instantiation. So to do the module instantiation, I have to follow the order which I have already explained. First I have to write the name of the module which I want to instantiate. This 1-bit full adder, you remember we had named it as FA, so I have to write exactly the same name. Otherwise this module will not be coming into the top level block. Then some label. I look at my diagram, it's the first instance is named as FA0, so I have to repeat that label FA0. Then inside the bracket I am writing any port of my subblock. So here this is the subblock I am dealing with. So I am taking one port of that subblock, say A, dot A is connected to A of 0. The meaning of this is the port by name A of my subblock is getting connected to the port A of 0 of my top level block. Then comes B is getting connected to B of 0, B is getting connected to B of 0, C in is getting connected to capital C in, okay, C in of my subblock FA0 is getting connected to capital C in of my ripple carry adder, sum of my subblock is getting connected to sum 0 of my top level block. Similarly, C out, as you can see in the picture, is getting connected to an internal wire called C1. So you are very much free to write here wire C1, C2, C3. Okay, that resolves the doubt how from where C1, C2, C3 are coming. But as I told, wire is the default data type, so even if you miss to write it, nothing will happen. The Verilog will assume it to be of type wire only. Okay. Now what I have just now finished is instantiating one 1-bit full adder FA by name FA0 and establishing connection as per this structure given. Now I have to repeat it for 3 more instances by name FA1, FA2 and FA3, and that is what we have to do now. So FA1 is the next instance. Here A is getting connected to A of 1, B is getting connected to B of 1, sum is getting connected to sum of 1, C in is getting connected to C1, C out is getting connected to C2. Now 2 more instances with the connection exactly as per the structure which is given to you. So once we have established all these interconnections, we are good to write the end module. But I caution you, for this particular design to work, the precondition is that you must have already written, okay, you must have already written the 1-bit full adder which you are trying to instantiate in the same library of the tool to which you are trying to instantiate this particular block. Otherwise, while you are calling here the 1-bit full adder, the compiler will give you an error, object not found. So what is the precondition? Whenever you are instantiating a sub block to a top level block, the sub block must be already available in the library in the pre-compiled form. Okay. Now let us, what we have just now see is by port name. Okay. Now let's see how we will do the same with the help of port order. Okay. So when you are declaring something based on port order, you must be very much aware about how the ports are declared in the subblock. Now here we have declared the ports in this order, in the 1-bit full adder, A, B, C in, some, C out. So So you have to write the things exactly in the same order. Just a minute. Just a minute. Yeah. So here, as normal, everything is normal, just like in the previous example. But while we instantiate, there is a change. Here we are writing A of 0, B of 0, C in, sum of 0, C1. So the meaning is, what you are writing here, while you are instantiating, say, FA0, you are writing in its bracket the corresponding port of the top level block. So here the first port, you have written A of 0. The meaning of this is, the A of 0 port of the top level block will get connected to the first port in the sub block. So first port happens to be A. So A of 0 will get connected to A. It is same as writing dot A inside bracket A of 0. Okay. Similarly, B of 0 should get connected to small b. C in should get connected to small c in. Sum of 0 will get connected to small sum. C1 will get connected to C out. So this kind of connection or instantiation is called instantiation by port position or by port order. Okay, so repeat it thrice more for all the instances FA1, FA2, FA3. Replace these ports with the corresponding connections. For example, while you are instantiating the second instance FA1, okay, A of FA1 is getting connected to A of 1. B of FA1 should be getting connected to B of 1. C in of FA1 should get connected to C1. Sum of FA1 should get connected to sum of 1. C out of FA1 should get connected to C2. So this is how we do it while we are trying to instantiate a module by port order or by port position. Okay. So having discussed the hierarchical modeling concepts, we are ready to discuss the components of a simulation. Especially once the design is completed and functionally simulated, we are ready to verify the design. So this process of verifying the design is called application of stimulus or test bench. This is the simplest way of verifying a design. So there are two styles by which a stimulus or a test bench can be applied. One of the style is shown here, which we will be following. Here we will be describing a top level block called test bench. Okay, and to that test bench we will be instantiating the design under verification or design under test. Okay, and establishing connection so that the internal ports of this test bench will be working as a feed or the ports which are responsible for giving stimulus to the design under verification. And the DUV will be driving some internal wires of the test bench will be put for constant monitoring. So corresponding to each input given, the output will be generated and that will be compared to the truth table. If they are one and the same, the DUV is deemed to be correct, otherwise there will be some error. Okay, so let us see how this can be put to use in actual practice. Okay, so to do that, let us take an example. So in this example, we are taking a simple design under verification, say a simple simple 2 input AND gate written in data flow modeling. So as you know, we have discussed this program earlier. There are 2 ports A and B and 1 port output. A and B are wire. So it is out, and the functionality is out is nothing but A ampersand B. So this is a simple 2 input AND gate. Now we are going to write the test bench for that. So if you look at the test bench structure, basically it itself is a module without any terminal ports. Okay, then it will be carrying basically 4 components. One is declaration of its internal ports and wires. Then you have to instantiate the design to be verified. So in this case, the design to be verified is going to be AND2_DF, which is a 2 input AND gate. Then we will be generating the test patterns that will be driving this 2 input AND gate, and the test patterns are nothing but those input combination that will come in the truth table of that AND gate. Then we will be setting the output port of the design under constant monitoring. So once we have done all these things, the test bench description is complete, we are good to write the end module. So this you can use as a checklist once you write a test bench. Okay, so let us see how we actually write this one by one. So here we are going to describe the stimulus for this particular AND gate. So as normal, we have to write module name. Normally we write a list of terminal ports also, but you can see that test bench, we are going to write it in this way. This top level block don't have any connections going outside to the external world. Okay, so in this case also you don't find a terminal port list, you close it with a semicolon. Now the next step is about describing the internal wires and registers. So there are two ports for this my test bench. One is called capital A and B, and also there is an output port called wire, which is actually an internal port. So A and B I have declared as register and out as a wire to obey that port connection rules. The next thing what we do is instantiation of design to be verified. Okay, so as normal we write the name of the module to be instantiated. The name of our DUV module is actually AND2_DF. Then we will write some instance name or label. We have labeled it as DUV. Then inside the bracket I have written small a is to be connected to capital A. Capital A is the port of the test bench. Small a is the port of the DUV. Small b should be connected to capital B, and small out of my test bench, small out of my DUV will be connected to capital out wire of my test bench. So this is nothing but instantiation by port name of design under verification. So once this is done, what we'll be doing is we'll be setting the ports of the test bench under constant monitoring with the help of a keyword which we already discussed, a system task called monitor. So $sign monitor, as I already explained, is a system task in Verilog which once invoked will continuously monitor changes in the values of the variables in its sensitivity list. So as normal we write within a begin and end $sign monitor, then we list out the ports to be monitored. So inside quotation whatever we want to print we give it. So here it will be printing in the console area sim time equal to, and %g is an indication to the compiler that you expect to print a time value returned by another system task $time. Okay, then a comma will appear, b equal to will be printed, then the binary value returned by the a equal to will be printed, and the binary value returned by the variable a will be printed. A comma should appear and b equal to will be printed, then the binary value returned by the variable b will be printed. Then comes a comma, out equal to will be printed, and the binary value returned by out will be printed. So here b means expect a binary value. If you had given a d, it will print the value in decimal. G means time value, then O means value in octal, H means value in hexadecimal, and so on. We discussed it already. So what we have done the fourth step which is listed here, monitoring of the output. Okay, so we have used monitor. What is the peculiarity of monitor? Monitor is a system task which once invoked will continuously monitor changes in the values of the variables in its sensitivity list. Okay, then we have to do one more part which is test pattern generation, for which I am writing another initial, and inside a begin and end I am feeding it with all possible values which an AND gate should take legally. For example, I have given an inter assignment delay of 5 simulation time unit. So after 5 simulation time unit I am making a equal to 0, b equal to 0. Then after another 5 nanosecond or 5 simulation time unit, that is 5 plus 5, 10 simulation time units I am making a equal to 0, b equal to 1. Then at 15 nanosecond I am making a equal to 1, b equal to 0, and at 20 nanosecond I am making a equal to 1 and b equal to 1. So once I am done, I am right to write an end and end module. So that completes my test bench description. Now if you look at the checklist which is shown on the right side, you can see declaration of A, B and out as corresponding data type. If you examine here, you can see the value of A and B are changing only occasionally. Until and unless they are driven with a new value, they should hold the value temporarily. That is the reason why I have written A and B as register, whereas out is being continuously driven, okay, by the gate. Okay, so it's a continuous assignment, that's why it has been declared as wire. Okay, so data type declaration is completed, then instantiation of the DUV is done in this step, then test pattern generations are done in this step, and monitoring of input output are done in this step. So monitoring of input and output can be given, not just output. So if you write this program, and already if you have this DUV in a pre-compiled form in the same library, on running this test bench module, you must be expecting to get an output like this. For example, sim time is equal to, you are getting A equal to X, B equal to X, and out equal to X. What is the reason? The reason is that you can see here at 5 simulation time, at 0 simulation time unit, you don't have any value for A and B. So A and B will be getting its default value, and A and B being declared as a register, the default value would be X. Okay, so that is what we are getting in the output. Okay, and out is being continuously driven with the value of A ampersand B, which would be X ampersand X. We are getting X. At 5 simulation time starts our assignment. We are making both A and B go 0, and the result will be 0. At 10, A is 0, B is 1, and the output is 0. At 15, A equal to 1, B equal to 0, the result is again 0. At 20 nanosecond, both are 1 and output is 1. So because this exactly matches with an AND gate behavior, truth table, we can deem our design is correct. So that is how we do simple design verifications. Okay. Now you can, as an exercise, you may try out writing a test bench for a ripple carry adder, which we have described with ports A, B, C in, and sum and C out. Okay, something like this: module name, declaration of the ports. Then you have to instantiate the thing, instantiate by port name. That's a good practice. Then set the ports of the test bench, that is capital A, capital B, capital C in, sum and C out for constant monitoring. Then feed it with some meaningful test vectors and simulate and get the waveform and the biorhythm. So it is left as an example. One template is given, you may try it out. Now having done it, we are ready to close this session. So in a summary, we have seen the design methodology, basically the top down as well as bottom up approach, the pros and cons of each one. We have also seen the connection rules whenever we are doing inter-module connections, how the ports should be connected. Then we have also seen hierarchical modeling example by taking the case of a 4-bit triple carry adder made out of 4 instances of 1-bit full adders. We have also seen the syntax for port instantiation. We have seen how port instantiation by, module instantiation by port name is done, and module instantiation by port order is done. We have also seen how design verification can be done with the help of simple test bench, borrowing the concept of hierarchical modeling. So that completes this session. Thank you.